Okay, let's continue in chapter 17. The next topic is phase changes. What happens when we are going from solid to liquid? We call that melting, from liquid to gas, vaporization, and we can go backward from gas to a liquid, condensation, right, and from liquid to a solid, freezing. Now let's see what happens when we're going from here to here. Imagine that we have ice, right, at 0 Celsius. All right, so this is ice at 0 Celsius. 0 Celsius. What happens when we add, right, heat? Well, if we add heat, the solid becomes to liquid. So we start melting the ice. Imagine that we need some heat to melt, let's say, 1 kilogram of ice. What happens if we increase the amount of ice? In this case, we have 2 kilograms of ice at the same thing, 0 Celsius. We need to add some heat. Of course, if we increase the amount of mass, in this case of ice, we need more heat to melt it. Conclusion, well, heat is proportional to the amount of mass. How do we eliminate this symbol? Using a constant. So heat is equals to a constant called heat of fusion, right, times the mass. So we have that heat of fusion is equals to heat divided by mass. Sometimes this is called latent heat of fusion. Okay, perfect. Let's see what happens when we're going from here to here. In this case, we have water at 100 Celsius. And the same thing, let's add some heat, right, to make this water gas or vapor or steam. Okay, great. Imagine that for this case we have the same thing, 1 kilogram of water at 100 Celsius. Let's increase the amount of water. In this case, one more time, is water at 100 Celsius, but now it's 2 kilograms. Also, we want to vaporize this amount of water, so we add heat, right? We add some heat. Now let's compare these two cases. Well, if we increase the mass of water, of course, we need to increase the amount of heat, right, used to be to vaporize this amount of water, correct? So the same thing as before, heat is proportional to the mass. If we increase the mass to be vaporized, we must increase the heat added to the system. Okay, the same thing as before, so we need to use a constant. In this case, this is the latent heat or heat of vaporization times the mass, correct? So heat of vaporization equals to heat added times the mass. Okay, but we can go backward now. The same thing, right? We're going backward, we need to remove this amount of heat. Again, we're going from here to here, we add this amount of heat. If we're going backward, we have to remove the same amount, right, for these cases. Got it? Perfect. Now, for water, which is the most important substance that we have, right, in this analysis, is found, for example, that if we have water, right, at let's say 0 Celsius. Imagine this is 1 kilogram of water, 0 Celsius. In this case, requires right some heat to melt the ice at 0 Celsius. Requires this amount of heat, which is 3.34 times 10 to the 5th joules, right, to form right the same amount of mass, in this case water, at the same temperature, right? 1 kilogram of water at, in this case, it's not water, in this case is ice, sorry, it's gonna be ice, and this is gonna be water at 0 Celsius, correct? And we can go backward. In this case, we have water at 0 Celsius, and we want to create ice, so we need to remove the same amount of heat, right? So this yield, correct, to form the same amount of ice, right, at the same temperature, 0 Celsius. Also, we can go from here to here, correct? That's for water. The same thing, 1 kilogram of water, in this case water, at 100 Celsius, right, requires, correct, this amount of heat. In this case is 2.26 times 10 to the 6 joules to form the same amount of steam, 1 kilogram, correct, of steam at 100 Celsius. We can go power 2, right, in the same way as we did for this case, correct? Okay, this is gonna be for water. Now let's take the whole picture and see what happens when we have ice at temperature below 0 and we go to steam at temperature more than 100 Celsius. Let's see how the steps looks like. Okay, let's do it. Oops. In this case, this is very common in chemistry. You took chemistry, you are familiar then to this graph. At the beginning, we have temperature and we have heat, right? Heat right here, and this is temperature in Celsius. Imagine at the beginning we have ice at 20 degrees below 0 Celsius, and then we have 0 Celsius, and then we have 100 Celsius, correct? So when we add heat to the ice, where the temperature increases until it reaches 0. After that, it stays at constant temperature until all the ice is melted, right? It becomes water at 0 Celsius. Later, if we add heat, well, the temperature increases until it reaches 100, and then water is boiling, right? When water is boiling, it stays right at the same temperature until all the water is converted into steam. After that, if we add more heat, correct, the temperature of the steam increases even more. Okay, let's see. On this stage, what do we have? We have ice only. Right here, what do we have? We have ice and water, correct? Right here, what do we have? We have water only. Right here, what do we have? We have water and steam, right? And right here, what do we have? Steam only. Okay, these are all the stages that are followed for most of the substances. In this case, the simplest one is water. Okay, what do we have then in this case? So the heat added is equals to what? Is equals to specific heat of ice, right, times mass of ice times change in temperature. What about this stage? In this stage, we have that the change of phase. So it's gonna be equals to mass times latent heat of fusion, or heat of fusion. Okay, on this stage, what do we have? Well, we have that heat added is equals to specific capacity of water, right, times mass of water times change in temperature, correct? And right here, what do we have? Right here, we have the change, the phase change, correct? And this is heat 4 equals to mass of water times heat of vaporization. And finally, right here, what do we have? Right here, we have that heat is equals to specific capacity or heat, specific heat for steam, steam times mass of the steam times change in temperature of the steam, correct? So in general, what do we have? In general, we have that the torque heat is equals to heat 1 plus heat 2 plus heat 3 plus heat 4 plus heat 5, right? When we're going from here to here. We have another way how we present these steps. Imagine we have Right here we have ice, right? Ice at 20 below zero, and then we have the next stage is what? Water, ice and water, right? Ice and water. Actually, it's ice at 0 Celsius. And then what do we have right here? We have water at 0 Celsius. And then what should be the next step? Let's say water at 100 Celsius. And then we have steam only, right? Steam at 100 Celsius. And then finally we have steam, let's say at 120 Celsius. Imagine. Okay, perfect. So what do we have from here to here? From here to here, again, we have that heat is equals the heat added is specific heat of ice times mass times delta T. We're gonna be the same thing right here, right? The next one's gonna be mass times heat of fusion from here to here. Gonna be specific heat specific specific heat for water times mass of water times delta T. Correct. From here to here is gonna be change of phase from liquid to gas, and this is mass times latent heat of vaporization. And finally, right, we have specific heat for steam, correct, times mass times delta T. We have the same information in these two ways to represent, right, what happens when we add heat to a substance. Well, we have two cases. One case is that the temperature increases or changes, and another case that the heat is used to make the change of phase, right, from solid to liquid and from liquid to gas. Correct? Perfect. Okay, and we have a general formula for this set of stages, and the formula, the general one, is gonna be the sum of all specific heat times mass times change in temperature plus the sum, correct, will be plus minus in this case, plus minus, or plus right here, plus minus m the latent heat, or heat of vaporization, or heat of fusion, correct, must be equals to 0. Must be equals to 0. And this is the equation that we use to work on these processes, right? This is very common in physics and chemistry, right? When we're looking, for example, for a specific heat of a unknown substance, right? Or when we're looking for final temperature when we are using mixtures, right? When we mixed substances, correct? Combined substances, and they have different temperature, and at the end they make an equilibrium, and we can find, for example, the final temperature, or we can find also the specific heat for an unknown substance, correct? And this is the formula is used, right? It's another formula that is used. It says heat lost is equals to negative heat gained, correct? And at the end, what do we have? That heat, let's say, lost plus heat gained is equals to 0, correct? Which gives us the same idea as this one, right? It's just conservation of energy. If a substance is gaining, we have two objects in contact, right? One is gaining heat and the other one is losing heat, correct? But we have conservation of energy. The heat is the same. The heat lost by one substance is the same heat gained by the other substance. And at the end, they're in contact, right? Isolated and constant. They get in equilibrium. Both, right, have at the end a final temperature, the same final temperature, correct? And we use these formulas to find that final temperature or a specific heat of an unknown substance. Okay, we do this later when we go to the section for solving problems. Okay, perfect. Now let's go to the next section. The next section is gonna be the heat transfer. Let's go to heat transfer. Okay, heat transfer. We have in general three ways of heat transfer. Heat transfer. Heat transfer. We have three ways, mainly three ways. We have by conduction, by convection, right, and by radiation. Okay, the first one, by conduction. Imagine that we have a solid. It works mainly for solid and liquids, right? We have right here a heat addict, right? So what happens to heat? Heat is transferred right from this point to the other end, from this end to this end, right? This is by conduction. By convection, mainly for fluid, liquid and gases, correct? Imagine that we have this candle right here. So we have air. This air becomes hot, right? The hot air goes up and cool air is going right down. And we have convection, right? Perfect. And by radiation, imagine that we have the sun right here, the sun, and we have the earth, right? We don't need a medium to transfer heat, right? The heat is transferred by radiation. Okay, so these are the three ways how we can transfer heat. It's another one which is vaporization, but well, we take mainly these three. Okay, let's try to find a formula that help us, especially using conduction and radiation. We have very important formulas for these two cases. Okay, let's try to find those formulas. Great. When we're dealing with conduction, right, heat transfer by conduction, imagine that we have this slab right here, like this, correct? Imagine. So we have this area right here, one area, and we have this thickness L. And right here, let's take this, the sides, right, are a different temperature. Let's say this is at cool temperature. In the other side, right behind, right, is gonna be at hot temperature. So we have heat coming or transfer from, let's say, from TH to TC. This is cold temperature and hot temperature, correct? Perfect. Now let's see what happens. How heat is transferred from one side to the other side. Well, if we increase the area, of course we increase the amount of heat, correct, being transferred. So heat depends on the area, okay? Imagine that all the heat is being transferred only through this area. Don't worry about these areas outside. Okay, perfect. What about if we increase the length? If you increase the length, the thickness, of course, heat decreases, correct? Heat is inversely proportional to the length. Perfect. Now, what happens if we increase the change in temperature? Imagine at the beginning this is 20, well, this is 20, this is 10. Well, we have some heat transfer. Now, what happens? This is 80, this is 20. Well, more heat is being transferred, correct? So heat also is proportional to the change in temperature. These are the factors that are acting on the transfer of heat from one side to the other side. So these factors must be multiplied, right? When we're dealing with multiplication, we call, right, these numbers factors. So they're supposed to be multiplied. So what happened at the end? So we have heat is proportional to the area, right? Cross-sectional area, correct? Change in temperature divided by L, right? Our factors. Perfect. Now we don't want this symbol, we want equations. So we need to eliminate this symbol. To do that, we need a constant, because that constant is carrying carrying out the unit. So we need to match the unit. Okay, again, so in this case, heat is equals to a constant. The constant is called kappa, right? Times area times delta T divided by L. Correct? But look, remember how do we define specific heat? We said heat is equals to what? C specific heat mass delta T. But in general, this heat is heat transfer, must be heat in motion, right? It's changing. So we can say that then that the infinitesimal change of heat is equals to C specific heat time mass times dt. We can represent this quantity in this way. The same thing happens right here, right? We can say that this heat transfer, right, is equals to kappa. Kappa is actually the constant of proportionality, correct? And this is equals to, well, this depends on the material, right? It depends on the material. Depends on the material, correct? Also, because we are looking for the rate actually, this becomes the rate, right, in time, or the change in time, correct, for of these quantities. And this is called the heat current, right? Heat current, because now our heat is taking as a let's say as a substance and moves from one point to another point, like a current, electrical current, or current of water, correct? So what do we have? We define this quantity equals to H, which is just the heat current, right? Heat current. So heat current is equals to this change in heat, right, respect to time. This is how much heat is transferred, right? Perfect. So when we apply that condition right here, so we have that this heat current is equals to K, correct? It's not K, it's kappa. It's kappa times area times change in temperature divided by L. Correct? Perfect. And that's the formula that we use for heat transfer by conduction. Okay, great. Also, this quantity, delta T, right, then changes over L, which is equals to what? TH over TC over L, has a special name. This is called the temperature gradient, right? Temperature gradient. Temperature gradient. Okay, because it's going to give us actually the direction of which, right, heat is moving from always from hot to cold systems, correct? That's why we call it that, the gradient. Perfect. Also, look, we were dealing with a one direction is x direction and small changes, correct? We can represent this quantity in this way, right? The heat current is equals to kappa, right? Area times change in temperature, dx, correct? We can also use this equation, okay? And the same thing, this quantity is called, right, the temperature gradient. Usually in calculus we use that one, right? The gradient, the derivative, right, respect to a space position. Okay, perfect. So we have this other quantity, correct? Our equation is equals to kappa area times right, this temperature gradient, correct? Like that. Perfect. So these are again some of the equations that are found and that we have so far, correct? Perfect. Now, imagine that we want to use the quantities that are used in engineering, right? When we're looking for thermal insulation. Okay, there's a quantity called the thermal resistance, right? This is R. R is called the thermal, right? Resistance, correct? Thermal resistance, and the thermal resistance is defined as is defined as A over L over K, right? L over kappa. So definition, right? The definition. This is the thermal resistance. Correct. Is L over kappa. If we apply this right here, what do we have? Look, we have this heat current is equals to kappa A delta T right over L. Correct. Look, we have this quantity similar to that one, but this is the inverse. Correct. So this equals to what? It's equals to area delta T over right R, the thermal resistance. Correct. And this is the case when we have only one slab, right? Only one slab like this, correct? What happens if now we have two? If we have two, in this case, the total current, heat current, correct, is gonna be equals to, in this case, the total heat current gonna be equals to area. Imagine I have the same area, both slabs right here, times delta T divided by R1 plus R2. Okay, so in general we have this formula that help us to work with these problems, correct? Area, change in temperature divided by R1 plus R2. If we have 3, okay, plus R3, right, plus R3 plus and so on. Correct. Perfect. Okay, and this is these are the formulas used for heat transfer by conduction. Now let's go to heat transfer by radiation. Okay, we have only one formula right here. This formula is found again from the experiment, correct, from the experiment, and this is equals to by radiation, the heat radiated, right, or current heat, right, is equals to area, right, E, which is the emissivity, times sigma, which is a constant, Stefan Boltzmann constant, times T to the 4th power. Okay, so it's gonna be for radiation. The energy radiated by an object depends on the surface, right? Depends on its temperature at the 4th power, correct? Depends on the material, correct? This is a constant of proportionality. In this case, it's gonna be the Stefan Boltzmann's constant. Great. In this case, E, right? Emissivity. It's called emissivity. And takes the value from 0, right, to 1. And as sigma is the Stefan Boltzmann constant, and this is equals to 5.67 times 10 to the -8, correct, watts per meter square, right, Kelvin to the 4th power. This is the Stefan Boltzmann constant, correct? And this is again the formula is used in in radiation. Okay, perfect. And with this information, we finish chapter 17. Now the next session is gonna be solving problems. Let's apply, right, these formulas. Okay, well, I'll see you in the next chapter. See you later. Bye.